Yes, we can hear you.
Perfect. So my speech is learning how to use variable renewable energy is the key to greening metal production. And firstly, I want to take a big picture look at this before we give a case example of aluminium smelters, because we need to understand where aluminium smelters fit into the grid and what is going to happen with the future of the grid. So the problem that we all face in metal production over the next 20, 30 years is that slowly, as other sectors decarbonise, it leaves industry as the largest single source of CO2 emissions. And so to decarbonise the planet and to meet our CO2 goals, we have to electrify industry. So currently there is an enormous amount of energy used as industrial energy. 74% of that is in heat. And Alessio just talked about using heat in several different parts of his speech. But to give you the size of the numbers that need to come in to be electrified is, of this heat, only 10% is currently electrified. So 85 EJ, if you took minus 10%, which is already currently electrified, to put that in gigawatt hours, that's about 23 million gigawatt hours. That's how big the grid will need to be if we are to electrify industry. That's about roughly 100 times what Australia produces in electricity today, and it's about 5 times what we produce as a planet today. So over the next 30 years, we're faced with finding 5 times more electricity than we generate today. And some of that electrification will, say, for example, for very high heat, may come through, and you've heard this, hydrogen, where we use renewable energy to generate hydrogen, and we burn hydrogen directly to get the heat we need. So that's part of electrification. So there's this enormous demand going to come in to the electrification of the world if we are to meet our CO2 targets. But there is a problem, is intermittency comes hand in hand with renewable generation. And you'll see, these were some figures I was playing with. I was reading some reports and pulled these 2 graphs out to show you side by side. So this is on the left-hand side, installed capacity of wind generation in Germany. And when you look at that chart, that's very reassuring. You say, oh, it's great, it's going up. But actually on the right was the actual generation from wind over a period 2011 to 2018. And you'll see the problem is that low-cost variable renewable energy is in that. It's variable. And so there was a statement from one of my colleagues, Dr. Linda Wright. She wrote some years ago that we all must fundamentally change the way we consume electricity. And that's what we face with. So we're going to look at a case study now of aluminium smelters. And this is in Australia. We use Australia as an example, but you could take any mixed energy grid in the world and you're facing the same problem. Australia is not alone. We've gone and talked to aluminium smelters and grids all around the world, from South Africa to Romania to Greece to everywhere. Everyone's facing the same problem, with the exceptions of Iceland and Canada and New Zealand. But even they have got problems because these normally reliable sources of hydro have suffered drought years, and so which we expect or can predict to be to get worse over the future. So, and when we're talking CO2 emissions from aluminium smelting, Alessio had a figure up there showing the ratio, but it's roughly about 80% of the emissions, CO2 emissions from aluminium smelting globally, are from electricity production. And there's currently about 27% of aluminium is made from renewable sources, essentially hydro. That figure used to be 50%, by the way. So we've been burning more coal to make more aluminium. And I was at a conference in Europe when a professor got up and said that aluminium smelting is actually producers of CO2 that produce aluminium on the side. And the real thing is we need to learn for that not to be the case. So what's happened in Australia is that the smelters were built at a time when we were building big coal-fired power stations, and there was the economics of baseload. That is, a person would have a big asset, and they knew that one client would take a consistent amount of power from that asset, and it gave them a value of baseload. Then they could make their money from the rest of it. And so it was a win-win for the smelters and the generators at the time. And by the way, it allowed us to build nations on the back of that. So, we built our countries on the back of that sort of relationship and those fossil fuels burning. And so smelters were a cornerstone, and it was a symbiotic win-win. But now the value of baseload has been eroded, and in Australia, I would say it's eroded to zero. There is no value in baseload. Where the value is in flexibility. And most Australians will be aware of the Hornsdale battery, the Tesla battery, and how that works and how it saved the grid, and the value is become in flexibility. So what smelters need to do to be able to exist in this modern environment is to be flexible with their energy use. Fortunately, there is a relatively cheap retrofittable technology that allows smelters to be flexible in energy use and therefore become virtual power plants for the grid. And if they do that, they can then once again become a corner stakeholder for every variable renewable energy grid. And this is more of a cohesive win-win. And the four wins in there is it's a win for the generator, it's a win for the smelter, it's a win for the governments trying to lower CO2 emissions in grids, and it's a win for the people at home who in New Zealand, we keep the heaters on in winter, but you could say keep the air conditioning on in summer. And so that's a cohesive opportunity for aluminium smelting, not only to lower its CO2, but to be able to provide society a value. Briefly, we'll go through how NPOT works. NPOT is the heat exchanger technology that's retrofittable to the aluminium reduction cells that allows it to variable its energy use. And for those unfamiliar with aluminium smelting, the process was invented 125 years ago, and essentially it's still the same today. And somebody, Dr. Mark Doreen, said to me, that's because it was a very good process to start with. So, but it's been a process where it's relied on the constant use of electricity to do two jobs. One is for the electrochemical reduction process to make metallic aluminium from alumina, but the other is to actually retain heat in the cell, a critical balance. I won't go into why that is, but it's to do with the cryolite used, and it essentially has to have its own ledge of colder cryolite, a little bit like a candle burning where there's hot wax around the flame, but the cold wax keeps the hot wax in the cell. Well, the same thing with an aluminium reduction cell. The colder cryolite keeps the molten cryolite in the middle. So approximately half, Alessio said 40%, but it's approximately half the energy consumed in an aluminium reduction cell is used to make metal, while the other half must be lost as heat. Okay, it must be lost to be able to get that heat balance. So the NPOT installation It's really rather simple. It's very smart in what it does, but it's really a set of piping. It's got one moving part, an extraction fan outside, and it's got no electronics other than the fan, which in Germany, in Trimet, they operate off a smartphone. And so the fan creates a negative airflow, and it draws ambient air from the basement through a set of exchangers that are mounted on the side of the pot, and are optimized for air turbulence, and extracts that air out. Now, when you put anything on the side of the pot, you've suddenly insulated it. So it must run a little bit of air to get back to its neutral point. And then if you want to increase production by increasing energy use, you can turn the fan up and it increases the cooling. So you can go up in production. But you can also turn the fan down and it's packed with insulation. And what that allows is it allows you to reduce the energy in the cell, reduce production accordingly, but it allows you to modulate. Therefore, you can modulate both up and down. So here we go. We look at with MPOT in a cooling mode, you can go up to 30% up in production. Now, there's a caveat there, is that most smelters will probably have a ceiling, an energy a ceiling where something will stop them going up to that amount of energy. Rectifiers, bus bars, magnetic compensation. They would probably have to undergo an upgrade to get that full 30%. But the MPOT system does it. It's just their limitations may not let you go up that much. And to go down, all smelters should be able to go down as much as 30%. And that just by reducing fan speed. Some smelters would want to step down. They might be able to do 20 instantly and another 10 over a period of a week for such a thing as a seasonal downturn. So you decrease, if you're going down, you decrease the amperage, decrease in production, you decrease the cooling requirement, decrease the airflow, and the pot remains in balance. Doesn't alter the chemical process at all, doesn't alter the internal heat of the pot or the balance in the pot, and the system's retrofittable and it's non-invasive. It's actually sprung loaded onto the side of the pot. So what this allows, it allows hourly, daily, weekly, or seasonal power modulation. And so this graph shows a normal operation at 300 kA, and it could go up. We've put 20% here because it's an instant thing. Remember, you could go the extra 10 if you stepped up or stepped down. And you could go up in use when high energy, when electricity cost is low. Now, one of the things about a grid heavy with renewables, and we're talking about variable renewables, so that's mainly wind and solar, is that there is often times of excess production. The UK last year paid £167 million to its wind farms to switch off because there was too much electricity in the grid. Now, you could look at that and say, what economic benefit, how many jobs could have been created, exports, etc., could have been created with that £167 million of electricity that was asked to switch off. So going up in energy use, and this will be one of the drivers of industry. And it's one of the reasons that industry the efficiencies of or the low-cost renewables are suddenly competitive with direct burning of fossil fuels. So for the first time. So the reason why a lot of processes haven't been electrified, electricity was too expensive. It was cheaper just to burn coal and diesel and fuel by itself. But for the first time, renewables allow this to be competitive. And so you will get times where there's excess generation. But also, there are times where there's not enough generation for demand, and you can go down in energy consumption 20%. And you can swing up and down as many times as you like within that range. So if we take the bigger view of where this fits in, and this is an Australian example, by the way, so you can have a look at it. We've just rounded up the the smelter size to 1,000 megawatts to give you a generic smelter, a big one, or a medium-sized one for on a global scale. So these are comparison costs of low CO2, peak net load reduction. Now, why peak net load reduction is important is the IEA in their China Power Systems report came out and said, if you have demand-side response, is what we call this, you'll get a cheaper grid, 3% cheaper to operate, but massively cheaper in capital because you don't have to build this other generation that would sit around and be idle otherwise. So we're going to compare the costs of using an aluminium smelter as a virtual power plant compared to these other forms of where you could get 200 megawatts from. So aluminium smelter at the bottom, modulating aluminium's demand-side response. Some people call it demand-side management. It's the same term. Capital cost to retrofit with NPOTs around 70 million Australian dollars for 200 megawatts. The operating cost, i.e. what the smelter gets, is the energy arbitrage. And the energy arbitrage, we worked out that a smelter would make around $1,320 for every tonne of aluminium they didn't make. That would be the most profitable aluminium they ever made was the aluminium they didn't make if they just swung the energy arbitrage of 200 megawatts. The advantages, the duration can be as long or as short as required. Because the pot's in balance, you can turn it down for 24 hours, a week, 3 weeks if you've got a heat wave. Or if you're in a place like New Zealand where we have droughts and we're mostly hydro, then you could turn it down for a season. So pump hydro to get the same 200 megawatts is a capital cost of 450 million. A gas turbine will cost you 200 million plus the burning of the gas. A grid level battery will cost you 640 million to get 200 megawatts for 4 hours. And solar or wind would cost you 280 million, but there's a problem with that, is it may not be available. So the cheapest form of energy storage or demand-side response for Australia would be to modulate its 4 aluminium smelters, by far. And if you look at size, Tesla battery, 100 megawatts for essentially 300 megawatt hours, and a smelter could do 200 megawatts indefinitely.
I'm sorry to interrupt. You have 1 more minute.
Thank you. So who benefits from this? Well, I said before that the smelters can benefit and have their energy arbitrage, $1,320 a tonne. But the power system, the avoided cost of generation is 732 million. And the cost for the 4 smelters in Australia, 200 million, roughly 200 million to go down, but the power system value is benefits by 700 million. That's a return of investment of 0.27 years. Okay, so just think about that. How fast and how expensive Snowy River is and how long it takes and what you could get from aluminium smelters. So CO2 savings, now we calculate this conservatively of about 11% of Australia's total emissions. And where we get that figure from is that for every megawatt of storage, you can displace 10 megawatts of coal generation with renewables. Now, it depends where you are on the penetration curve, the renewables penetration curve. Australia is way down the bottom. So you displace a lot of CO2 initially. As you get further up the curve, by the way, you displace less CO2, but it's far more valuable. And so just think about that. Using the 4 Australian smelters as virtual batteries could allow the decommissioning of enough coal to reduce Australia's total emissions by 11%. So the metals of the future will be greener. And the key is utilising low-cost variable renewable energy. It will require a new way of thinking. And I will say technology enables solutions, but only people solve the problem. So the future of aluminium smelters hinges on sourcing greener power supplies. We must learn to repower our smelters with renewable energy. These are two statements that have been in the Australian media in the last 10 days, in the last week. Any guesses who made them? It was the CEO of Rio Tinto Group. Thank you very much. That's my presentation.